Hello again, let's get started. Consider f of x equals the sinc of x. Remember guys, we defined the sinc of 0 to be 1. We defined the sinc of any other number to be sine x over x. For any non-zero number, that is, f of the sinc of that number is sine x over x. Okay? Now, what about doing the derivative of the sinc? Well, as long as we're not at 0 itself, we can just we can consider it to be equal to sine x over x, and we can do Lodi high, and we get this guy right here. Low is x, high is sine x, so low times d high, which is cosine x, minus the high term, which is the sine x, times d low, but d low is just 1. The derivative of x with respect to x is 1, so 1 times and that just leaves sine x by himself, over low squared, so x squared. So, well, that was easy, but not too entertaining, really. But what about if x is not, what if x is indeed equal to 0? What if x is 0? Well, we can't use the shortcut rule this time because, well, we'd get 0 over 0. Like 0 here, sine of 0 is 0. Uh-oh. So no go there. We have to do it the old-fashioned limit way. So we do the limit as x goes to 0 of sinc x minus sinc 0 over x minus 0. Well, that's just sinc x minus 1 over x. And, well, but hey, remember the limit, we're not allowed to go to 0, but we get arbitrarily close to 0, so we can just consider the sinc to be sine x over x. So that's just sine x over x minus 1 over x. And then I get a common denominator. I turn 1 into x over x. And I bring the numerator together over x. Now, by the laws of algebra, I bring this x down together and multiply it into this x and get x squared. And the sine x minus x just stays up there. So I have the limit as x goes to 0 of this guy right here. As it turns out, this limit equals 0, but I've not yet given you the machinery to do this limit. You're going to need a thing called L'Hopital's rule, and I've not given you that thing yet. So we'll say more on that later. For now, just take my word for it that this limit is 0, but you really need more information. I have not given you enough info yet, so just quench your thirst for this right now because it requires L'Hopital's rule. And I'm not giving you that yet, so just wait. But suffice it to say, it is differential, and the answer is 0, but you'll need L'Hopital to get that, and we'll do that later. So let's move on. Let's look at this guy right here. D by dx of this numerator over this denominator. Guys, this is just more Lodi high, and you just have you have the low is 1 plus cosine x. The high is x plus sine x. So here's low times d high minus the high term times d low over low squared. So we have just plain low. Now if you derivate the high, you remember the sum of the derivative is derivative of the sums. So derivate the sine, you get the cosine. Derivate the x, you get the 1. All right. And then minus high, and then d low, and then remember you derivate the cosine, you get negative sine. Now if you derivate 1, it just disappears to 0. Okay, so it's just negative sine. All right, and then over low squared. Okay, now we do FOIL. Remember, this is a difference of squares here. A plus b times a minus b is a squared minus b squared. So actually, no, excuse me, that's not difference of squares, that's perfect square. My bad. This is perfect square. A plus b times a plus b, well, that's a plus b parentheses squared. That's a squared plus 2ab plus b squared. Now, so we have cosine squared plus 2 times the cosine times 1, but multiplying by 1 doesn't change anything, plus 1 squared, which is 1. And then we minus, now be careful though, well, we're minusing, this minus is going to bump into this minus and give us a plus. So the minuses are going to disappear, so we just get a plus. distribute this sine x across this guy and this guy. So sine x times sine x is sine squared x, and then sine x times x is just, well, x sine x, right here. And then all that over low squared from before. Okay, now what can we combine here? Well, cosine squared here plus sine squared here is 1 by trigonometry. And then that one, and then 1 plus this one that was already here gives me a 2 right here. And that's really all I can do. That wasn't really all that earth-shattering. The other stuff has to just sort of stay as is. And just for neatness, I kept this times sign right here and right here. You can put a space between them if you'd rather. That would indicate multiplication just the same, but anyway. So, and there's that, and we're done. We just have this result right here. So that was just another example of Lodi-High. And, well, it grayed out on me again. Now this is a three-way product rule. What you do is, remember, if you have you remember we had f g prime plus f prime g. If you have f g h, it goes the way you think it ought to go. You'll have f prime g h plus f g prime h plus f g h prime. You derivate one of them and leave the other two alone. And you're going to have 3 of those sums. Each guy gets its turn to get derivated. Like if you had 100 guys multiplied, well, it would be a long, long go. You would have you'd have 100 iterations to do. You would leave 99 of them alone, and you'd derivate one of them. And each guy would have his turn, so to speak, as far as the getting derivated is concerned. Each guy would have his turn to get derivated, whereas the other 99 would get left alone. So here's what we do. Well, okay, you could just pick whichever one you want to go first. So we'll let cosine go first. So x cubed sine x, and then we derivate the cosine. All right, and then plus x cubed cosine, we derivate the sine, and then plus sine cosine, we derivate the x cubed. So we had 3 go-arounds, and really this times sign here is superfluous. So what's going on is we're letting this guy have his turn, the cosine, and then the sine gets his turn, and then the x cubed gets his turn. Okay, and these times signs are kind of silly and superfluous. Well, no, they're not. It's kind of messy without them. Let me keep them. I don't, strictly speaking, have to have them, but it's just for neatness. Okay, so we have all that right there. And I hate how it wraps. Let me skip this down a line. So you get the idea. That's how it's going to go. And from there, you just use the power rule or the trigonometric differentiation rules, whichever one you need at the time. It's not going to be all that exciting. So, well, we'll get down to it. Let me see if I can change the font. This is irritating me to no end, but it may just have to be. Okay, now guys, sorry for the small font. I'll make it big again here in a minute. Well, if you can't read it, I better just make it big. I'll just have to wrap it. I'm sorry about that. So each guy gets its turn. We derivate the cosine, derivate the sine, derivate the x cubed. So let's go in and do the derivatives. We do have to, of course, execute the derivative. Now, if you derivate the cosine, you get neg sine. So x cubed times sine times negative sine is just put the negative sign in front. You get x cubed times sine squared. You got sine here, and this guy turns into you get a sine out of this guy along with the negative sign, but we already took care of that negative sign. We put it right there. Okay, and then plus, now if you derivate the sine, you just get the plain cosine. So it's just going to be x cubed cosine cosine, which is x cubed cosine squared. Uh-oh, did I forget my square? I sure did, didn't I? Sorry about that, guys. Oops. And then, well, what else can I really do? Oh, the third guy. Yep, I've got to do the third guy. So plus, now we leave sine and cosine alone, and we derivate x cubed by the power rule. That's just 3x squared, and by commutativity, we put it in front. And really, we're done. That's it. Now, what you could do is you can, well, we can't do anything with this third guy. If you wanted to, you could factor out an x cubed from just these first two terms only. You'd get cosine squared minus sine squared, and you could turn that into the cosine of 2x. Like what you would get is you'd have x cubed, the common x cubed, and you can, by trigonometry, you can turn, this is optional, you don't have to do this. This is algebra, this is trig and algebra, this isn't calculus. In particular, it's really just trig. I can turn like the negative, like really what these first two terms, this is x cubed cosine squared x minus x cubed sine squared x, and that's going to be x cubed cosine 2x. I just want to show off that we can do this, and if you ever have an ABCD choice test, I want you to recognize that you can do that. Now, you can't forget your other guy. Now, this guy's not going to change. There's not much we can do with him. That 3x squared sine x cosine x, you just kind of have to leave him be. Well, I tell you what, though, not really. You know what? The sine x cosine x, that can be thought of as 1/2 sine 1/2 of the sine of 2x. So what we got here, is we can we're multiplying that 3x squared by 1/2 sine of 2x. This is trigonometry. This isn't even really calculus anymore. I'm just wanting to show off that I can do this. I want you guys to get this right if you ever get an ABCD multiple choice test or homework, whatever. But guys, that by commutativity and all that 1/2 can be brought over here, that 3. We can drop these parentheses like a bad habit. And so if we bring that 1/2 over here and multiply it into that 3, we get 3/2. So no point being pretentious. Sorry. I didn't want to mix it. It's not behaving. So I want 3/2. Okay, and then sine 2x, and we can drop these parentheses are now kind of silly and superfluous. Let me get rid of that. So we can just put plain sine 2x. I mean, I could keep the parentheses around it, but that's kind of silly. So there's that. And you can do that, and that could also be in your ABCD multiple choice. Like if you ever take a college test or a standardized test and you see ABCD, they may put it now, guys. They may put it like I had it in the first place 5 minutes ago, but they may also put it like this right here. So do be aware. And you know what? Yikes! I forgot my x squared, didn't I? Sorry guys, I forgot my x squared. Oops. So we can't leave x squared out. Sorry about that. So put that x squared right here. Otherwise, we're done. I just I forget the easy stuff. Okay, that just was a copy and paste. So now, let me see if I can move this down. That's bothering me and it's making me mad. Let me see if I can move that down. Or is it going to give me just a headache and a hard time? And I'm going to move this or down. I don't like my stuff to line wrap. I mean, it's not awful, but it's just disagrees with my taste buds. Okay. And this right here, it skips a line that I don't like it doing. Let's see if I can, I'm going to shrink the font just to get it on the line there. Oh, it's been difficult. Oh, it's just been downright obnoxious. Okay, I had to font 12 it, guys, but I showed you what it was a minute ago. So there's that. Now, so you've seen all this already. I let it skip a line for a while so you could read it, but now I've had enough and I want to get this on one line. I just don't like stuff to skip lines. I'm not mad at you at all. I'm mad at my computer for skipping the line. Okay, sorry about that. All right, so now on your multiple choice test, you may see it in this form or you might see it in this form. You need to be ready for both. I know it's annoying to have to go back and refresh on trig, but do refresh, okay? I'm serious. Just please do, okay? Now we'll move on. Now d by dx of the natural log of the 6th root of x. Now remember, that's just the natural log of x to the 1/6 power, and by algebra 2, that 1/6 can jump. It jumps way out here in front of the log. But by calculus, it can jump way out here in front of the derivative. That 1/6 jumps all the way. It does a high jump. By algebra, it can jump in front of the natural log right here. And by the rules of calculus that we've already discussed, it can jump in front of this derivative right here. It's a constant. Remember, the derivative of a constant times something is just the constant times the derivative of that something. So the multiplicative constant can jump out in front of the derivative by calculus. It can jump in front of the natural log in it can jump from the exponent down to a coefficient in front of the natural log. That's by algebra 2. Remember, the ln of x to the 1/6 power is 1/6 ln x, and then by calculus, we take the 1/6 all the way out here, okay? Now remember, the derivative of the natural log, that's just 1 over x. I told you to take my word for that. We're not going to prove that. I don't think I'll prove it in this class. If I was in analysis, I would have to prove it. I don't want to do that here, or at least not likely. And now 1 over 6 times 1 over x, that's just, now you multiply the 1 times 1 up here and you get 1, multiply 6 times x down here and you get 6x, and that's all, 1 over 6x, okay? So that's all for that one. And I'll save my stuff and I'll repost this in your files that I got on video 1. But anyhow and anyway, now be careful. This guy right here is a very different beast. It's not the same thing, okay? And it does a line wrap right here. Let's see if I can fix that. As you can tell, I'm a little perfectionistic about some of this stuff. I guess you probably can tell by now. And let me see if it will behave or not. Will it behave? Yeah, it behaved reasonably well. Okay. So now this time, we're not raising x to the 1/6 power. We are raising the whole ln of x to the 1/6 power. We're taking x, we're taking the ln first thing, and then we're taking the 6th root after the fact. That wasn't true in the last problem, okay? It was not true at all, but it is true now. So what you got to do is a chain rule this time. You got to let u equal ln x. So you do d by du of u to the 1/6 times d by dx of my u term, which is ln x itself. Okay, and then by the power rule, that's 1/6 u to the negative 5/6, subtracting 1 off the exponent, and then times, now remember, derivating the natural log just gives you the 1 over x. All right, now guys, so remember that u to the negative 5/6, by algebra, it jumps down here with the 6 and becomes u to the positive 5/6. And also remember, by algebra, this x can come down here with it because it's down here in the denominator already. And this u to the negative 5/6, since it's a negative power, it's going to come down here and become positive powered. U to the positive 5/6. Okay, so now remember that x, this is correct, but we don't like a fractional power in the denominator. So we know that 5/6 plus 1/6 would give me 1, because 6/6 is 1. So what I need to do is stick a u to the 1/6 down here, but because I did that, I have to multiplicatively multiply the top by u to the 1/6 as well. I multiplied the bottom by u to the 1/6, I have to multiply the top by u to the 1/6. Now by associativity, I can go ahead and multiply the two u terms, and I get u. Okay, so I have 6xu down here. But guys, remember, I go ahead and take the liberty to replace u with ln x. So we have 6xu, but u is ln x. So I go ahead and just replace u with the ln of x. I don't think that was too brutal of a step to skip. I hope I didn't throw you off. I went ahead and replaced u with ln x. And u to the 1/6 power, yeah, sure, that's the 6th root of u, but u is the ln of x. And if skipping that step bothered you, I'm about to run out of time, but I could try to copy and paste it in here real quick. And I don't like to do too much toward the end of the video. So the step that I skipped, taking a step back, this ln x was just, it is u. So that u would have went there. U to the 1/6 is the 6th root of u. And the ln x, well, and remember we had u here first. We had the u's here and here. And then on the next step, we replace them with ln x's. This u to the 1/6 is the 6th root of u. And this is just u to the 1 now, which is u itself. And u itself is the ln of x. Guys, that'll be all for this video. Thanks. I'll see you on the next video. Bye-bye.